Welcome everyone. So today's presentation is going to be super short, yet extremely important. We are going to address what we call Simpson's paradox. Now, a paradox, as I'm sure you know, is a statement, is a concept or an idea that seems to be contradictory or absurd, weird. But then when you put it to a test, it just doesn't sit with your brain. But when you put it to a test, when you try to prove it, it turns out to be true, and therefore you cannot dismiss it. And Simpson's paradox shows up in so many walks of life. It shows up in everywhere. As you will see when you do your assignments, I'm going to ask you to go on the web and read more about it. A famous place where it shows up is in baseball. So imagine I have, I color-coded everything here so you don't get lost with all these numbers. So let's say we have two professional baseball players, player one and player two, and they're going to play the first season, and then a year later they're going to have another season, and of course they keep track of their numbers, just like any other sports. So player A, or player one, had 200 at-bats and had 120 hits. So that player has an average, we call it, now you know better, I call it the mean, but in baseball they call it the batting average, right? And what they really mean to say is the batting mean, because the average can also stand for the median and the mode. So the batting average, as you can tell, I made up the numbers to look cute. So 120 divided by 200, it's the same thing as 60 divided by 100, which is 60%, okay? Player 2, on the other hand, had 400 hits and 800 at-bat. So basically, this is half that. So the ratio is 50%. So the batting average for player 1 is 60%. And the batting average for player 2 is 50%. So clearly, player 1 did better than player 2 during the first season. So keep that in mind. Player 1 did better than player 2. So we go to the next season, just repeats. And the first player had 200 hits and 800 at-bat. That's basically 1/4 of that one. So that's 25%, right? 200 divided by 800 is exactly 25%. And player 2 had 20 hits and 200 at-bat. So 20 divided by 200, knock off 0, you get 2 divided by 20, or 10%. Okay? Or just divide both sides by 2. You get 10 out of 100, which is 10%. Once again, player 1 has a better batting average. So player 1 has a better batting average during the season 1, and player 1 again had a better batting average than player 2 during season 2. So clearly this guy did better during both seasons. Then what do we want to do in green is combine their at-bats and their hits, and that's how it actually works. So player 1 had 200 and 800, so had 1,000 at-bat. You see why I picked these numbers, just so that the numbers look cute. Player 2, on the other hand, had 800 and 200, had the same number of at-bats, 1,000. Now, player 1 had 120 hits and 200 hits. That's 320. Player 2 had 400 and 20. So that's 420. So what's the batting average? Well, 320 divided by 1,000, it's like 32 divided by 100, which is 32%. Player 2 had 420 hits out of 1,000 at-bat. Once again, knock off 10. You get 42 divided by 100, which is 42%. So take a pause on this now. So player 1 did better than player 2 during season 1. Player 1 did better than player 2 during season 2. But overall, who did better? Is that stunning to you? Is that surprising? It's not surprising. The math told me that player 2 did better when you combine their seasons. Yet, player 1 did better during season 1 and season 2. And I could have done 10 seasons where player 1 would do better, season 1, 2, 3, all the way to season 10. For 10 years, player 1 could do better. But overall, player 2 turns out to have a better batting average. So this phenomenon works when you see a huge difference in between the seasons. So you have in here small numbers, so to speak, as opposed to very high numbers. And in here, you have high numbers. That doesn't mean the ratio is big. The ratio is still small. But you have high numbers, and in here you have small numbers. So player 1 did better, player 1 did better, but overall player 2 did better. See, player 2 did better. So that is the idea of Simpson's paradox. I would love for you to go and read a lot more about this. There is a famous story from if I remember, from the 80s at Berkeley. UC Berkeley, if I remember correctly, what they did, they for their graduate admissions, a graduate like master's program and a PhD program, they admitted men more than women in many disciplines, let's say history and mathematics and so on and so forth. And the reason it turned out to be famous because somebody decided to sue Berkeley, and they thought they were biased toward women because they accepted a lot more men or graduate students who happened to be men than women. The whole thing went to courts, and not only that Berkeley, UC Berkeley Graduate Admissions Office did not discriminate against women. In fact, it turns out that I wouldn't say that they were favoring women, but women had an advantage over men. So what I would love for you to do, and this is a famous story that you should read about it. So what I would like you to do, two things. One, go online and read about this incidents from the 80s, and then write a short report. You could do it by hand, like a nice little paragraph of your understanding of what happened. So why did the judge find that UC Berkeley was not guilty? And what was the reasoning behind finding that actually women were not being discriminated against compared to men? Even though on the numbers, as you will see from tables, across many disciplines, like philosophy and geography and math and whatever, it seems to be that they were favoring men, but they were not. Okay, so read about it, write a report. I would say take no more than 5-10 minutes. So write the report, but I would love for you to read about this. Okay, so that's part of your assignments. And right underneath, I would like you to come up with your own scenario that reflects Simpson's paradox. I said here the only two exceptions is don't use baseball. So in other words, don't go here and just play with numbers. Like, okay, make this 100, make this 60. You're not coming up with your own. You've got to come up with your own. So the only two exceptions are the don't do baseball at all, even if you change the numbers, and don't just use the UC Berkeley incidents. And the world is yours. You can come up with your own story, or you can read. They show up a lot in medicine, by the way. You can read more about them and come up with your own story. Just write them on one page, one underneath the other, and then upload your assignments. So I want to conclude briefly with a brain teaser. So I have 9 dots here. Okay, and pretend this is like a square. These line up nicely, okay? And what I would like you to do is connect these 9 dots with 4 line segments, not curved, but they have to be straight, okay? Line segments, they have to be straight. You cannot curve, okay? without lifting your hand, but make sure that you connect all of them. So I'm going to work out a couple of examples for you so you know what I'm talking about. So let's say I'm going to try. I'm going to say 1, 2, 3, 4. I missed this one. Okay? Let's try again. Sorry, they need to line up nicely, okay? So I could do 1, 2, 3, 4. I skipped this one. I'll try again. And I'm going to give you hints. You know, I'm sure you've heard the expression, think outside of the box. Well, try that, okay? So let me try one more. 1, 2, 3, 4. I missed this one. So I failed. Fail. Fail. Try to succeed. Have fun with this, okay? If you would like to do this, you're never required to do the brain teaser, but it's fun. It really helps with the lateral thinking. So it just benefits you. It doesn't benefit anybody other than you. So have fun with this. Yeah, have a good one. Take care.